Hello everybody, and welcome to the beginning of section 2.6. We are looking at page 54 in the workbook, and the topic of this section is derivatives of inverse functions. So up to this point in the course, we've talked about a number of different ways of taking derivatives of functions. We've got a long list of derivative formulas, and we're going to add to it in this section using the concept of an inverse function. Okay, so let's start by just doing a brief review of the idea of an inverse function. Okay, so we're looking at this table facts about inverse functions. Let's start with point number 1 here. Okay, so it tells us that the point xy is on the graph of the function y equals f of x if and only if the point yx is on the graph of the inverse. This reminds us of the fact that graphically, an inverse function just reverses the ordered pairs that are on the graph of the original function. Okay, we can maybe look over here in the graph to the right and just give a quick visual example of that. Notice, for example, that the point 1, 2 is on the graph of f of x, according to this picture, and that 2, 1, the reverse of that, is on the inverse. Okay, and you could do this experiment with other points and you'd discover that the points on the graph of the inverse are all reverses of the points that are on the graph of f. Okay, now back over to the box to the left here. Okay, one other thing, you might remember this fact from algebra. Okay, the fact that functions and inverses undo each other. Okay, so for example, f inverse of f of x, that would just be x. It's like saying that f inverse undoes the function f and takes us back to the number x. And then it works in the other direction as well. F of f inverse of y is equal to y. Okay, so very brief review of some of the main points of an inverse function. We are ready now to look at example 1 here. Okay, let's read this together. So given to the right is the graph of f of x equals ln of x, the natural log function. They'd like us to first sketch a rough graph of the derivative and then to find a formula for the derivative. Okay, and first of all, ln of x is a function that we don't know how to take the derivative of yet, so that's what we're going to try to figure out in this example. Okay, and let's start with the graph of this. Okay, so we've got a graph of the natural log function, and notice that that function is increasing. Okay, so since f is an increasing function, we know that its derivative has to be above the x-axis. Okay, now there are a lot of different ways that we could draw the graph, though, and have it be above the x-axis. I'm going to give you 2 variations and ask you to decide which you think is the best match. Okay, let's clear some clutter away here. Okay, so one possibility for f prime is that maybe it looks like this. Okay, that's above the x-axis, but it might also look more like this. Okay, both of those are possibilities for the derivative because they're both above the x-axis. Which do you think fits better in our situation? Okay, well, we could maybe answer that question by drawing in some tangent lines, okay, because the derivative function, the y values are about slopes of tangent lines. Okay, and as you draw more and more tangent lines, what do you notice about the slopes as you go left to right? Are they getting bigger or smaller? Okay, the slopes are starting out really steep and they're getting smaller. You can think of the slopes as sort of approaching 0 as we go left to right. So what that means then is that the solid graph looks like a better fit. Okay, because it starts out with y values that are really positive and the y values get smaller. Okay, kind of matching the fact that our slopes are getting smaller. So let me get rid of the variation that doesn't fit so well. Okay, it looks like our best guess as to the general shape of the derivative would look like that. Okay, something that's positive but decreasing. Okay, and now we're ready to find the formula for this derivative. Okay, what would a derivative formula for the natural log of x look like? Okay, well, again, we don't have a derivative formula for the natural log of x, but we do know that the natural log function is the inverse of the exponential function. Okay, so we know then that e raised to the ln of x has to equal x. You might remember that fact from algebra, and it just comes from the fact that e and ln are inverse functions of each other. They cancel each other out. Okay, so that's an equation that's true, and so we are free to take the derivative of both sides. Okay, that's a legal operation if we do the same thing to both sides. And the nice thing about this is we know how to take the derivative of the exponential function e. Okay, so on the left-hand side, we're taking the derivative of e to the ln of x. This is a typical chain rule situation. We can think of that ln of x as being u. And so we need to take the derivative of the whole function, e to the u. How do you take the derivative of e to the u? You just get e to the u back again. Okay, so the derivative of the whole function is e to the u, and then the second part of the chain rule is to take the derivative of just the u. Okay, so we get e to the ln of x times the derivative of ln of x on the left. Okay, and over on the right-hand side, we're just taking the derivative of x. That's just 1. Okay, and let's see. If you look at what we've got now, notice that what we're trying to figure out is this, the part that I'm boxing in. We'd like a formula for the derivative of ln of x. So what we can do is just divide both sides by e to the ln of x to get the ddx of ln of x by itself. And what we get is, let's see, on the left-hand side, back up a minute. So what we've got on the left-hand side is the derivative of ln of x, and over on the right we've got 1 over e to the ln of x. And we might remind ourselves that e to the ln of x is just x. Okay, so notice what we've come up with here is a formula for the derivative of ln of x. Let's get rid of the middle part here and just write this as ddx of ln of x is 1 over x. Okay, there's our formula that we were looking for. Okay, and what do you think? How well does this formula match our picture? Okay, so if we've done everything right, that means that this f prime of x up here should be equal to what we got, 1 over x. Does this look like the graph of 1 over x to you? If you think about it for a minute, it does, because 1 over x is a function that gets smaller as x gets bigger. Okay, so nice graphical match to the formula that we just came up with.